Today let us continue discussing chemistry of group 14 elements. Other than carbon, we have silicon, germanium, tin and lead, and silicon is the most abundant element after oxygen in the earth's crust. And of course, the major source of silica is silicon is silica and also silicate minerals in the earth's crust, and germanium is least common and occurs in some zinc and silver ores in trace quantities and also in flue dust and the ashes of certain types of coal. And silicon and germanium do not show allotropic forms other than existing in the form of diamond like structures. And tin mainly occurs as cassiterite, that is SnO2, from which metallic tin is obtained by using one of the standard method of reduction. The main ore of lead is galena, that is sulphide ore. The composition is PbS, which is roasted in air to form lead oxide. Since we do not have a right reducing agent to directly convert into metal starting from sulphide, we are partially converting that one or fully converting that into corresponding oxide, which is then reduced to the metal using carbon monoxide in a blast furnace. Lead is a typical heavy metal, and when we look into the chemistry of group 14 elements, you may be surprised to know the fact that all group 14 members are fairly unreactive. That means, tin and lead dissolves in a number of oxidizing and non-oxidizing agents, whereas silica and germanium are only attacked by hydrofluoric acid, but all are reactive towards halogens. And graphite can form two types of products with either buckled or planar sheets depending on whether the pi system is disrupted or not. That means, when you react with graphite, when you react with other elements, if there is a disruption of pi electrons, that means adding another covalent bond, in that case what happens, it can buckle and it may take a cyclohexyl form instead of having hexagonal planar benzene for the rings. And of course, otherwise if it is not disrupted, nothing is going to happen, it remains the way it is in graphite. The reactions of graphite with fluorine at 400 degree centigrade gives graphite fluoride of composition CFXN. For example, when graphite is heated with fluorine gas at 400 degree centigrade, it leads to the formation of this one, and of course, here when N equals 1, it is essentially colorless. So, one of the possible structures for graphite fluoride is having fused cyclohexane type rings that I would show you later, and except for the edges of such sheets which will have CF2 units, that means each carbon would have 2 fluorine atoms. Otherwise, the central carbon atoms will have only one fluorine, and fluorinated graphite is non-conducting as pi electrons are consumed totally, and also the distance between the interlayers, that is between two graphite layers, increases and it becomes a good solid lubricant. When graphite is reacted with a reducing agent such as an alkali metal, for example, potassium, then such compounds are called inclusion compounds, and inclusion compounds can have a variety of ratios of potassium or sodium and carbon or even calcium. And in one such reaction, when graphite is heated or exposed to potassium vapors in the range of 100 to 320 degree centigrade, it gives a inclusion compound having composition of Kc8. That means, for every 8 carbon atoms there will be one potassium I will show you the structure of graphite fluoride. Here you can see graphite fluoride, you can see the plane of graphite and fluorine atoms coming out perpendicular to the plane. In other words, you can see here, because of removal of pi electrons and addition of fluorine atoms, it is no longer having sp2 hybridization. Now it is sp3 hybridization you can see for carbon. As a result, what happens, it is no longer a hexagonal planar ring. Instead, it will assume the cyclohexyl shape, and you can see in the diagram clearly all these things are puckered to have cyclohexyl interconnected cyclohexyl two-dimensional sheet. And now because of addition of fluorine, the graphite layers move apart from each other. To start with, we had about 335 picometers. Now after addition of fluorine atoms, the distance increases to 660 picometers, and as a result this is used as a solid lubricator. Okay. And structure of graphite is shown here. So these essentially are called inclusion compounds. Basically, if you pass potassium vapors into the graphite in the temperature range of about 100 to 320 degrees centigrade, you get inclusion compound having different ratios of alkali metals or alkaline earth metals with respect to carbon, and one such one I have shown here. And you can see this red lines are essentially representing graphite sheets, and then when potassium goes and sits between the two layers in this fashion, you can also see in this one here. Now the interlayer separation increases from 335 picometer to 540 picometer or 5.4 angstrom units as a result of the presence of potassium atoms in between. So that means in this one, for every potassium there are 8 carbons are there and ratio is 1:8, and probably this picture will show you the presence of potassium atoms between them. If you see carefully in the second diagram here, this purple color spheres are essentially representing, this purple color are representing potassium. You can see it is sitting on one layer on 4 carbon atoms, and if you look into similar inclusion compound of calcium, here the composition is CaC6, that is for every calcium there are 6 carbon atoms are there, and in this one the distance increases from 335 picometer to 452 picometers, and the carbon-carbon distance also increases from 1.42 or 142 picometers to 144 picometer. Let us look into the hydrides and organometallic compounds. In fact, methane is essentially a tetrahydride of carbon, and it looks very weird if we call methane as carbon tetrahydride. Nevertheless, its name is carbon tetrahydride. Let us continue using the name methane, and methane is the simplest hydride of carbon. The hydrides MH4 of other group 14 elements are less stable owing to the size mismatch between the group 14 atom and the very small hydrogen atom. That means, when you are thinking of making say SiH4, that is also called silane, silicon essentially uses 3s and 3p orbitals, and that has to form a hybrid sp3, and that should interact with 1s1. Since the size difference is enormous, what happens as a result of mismatch, the overlapping is not very efficient, and hence these bonds are very weak and also highly reactive. Same thing is true in case of heavier ones. In fact, germanium we are using 4s and it continues. Tin we use 5s and 5p, and in case of lead we are using 6s and p. So since the sizes are increasing enormously, the corresponding hydrides or element to hydrogen bonds also become much weaker and making them highly reactive. And silane and germane, that is SiH4 and GeH4, and also SnH4 called stannane are also known, but plumbane PbH4 is very unstable and no chemistry has been determined, and also it is very difficult to isolate and carry out reactions with plumbane. And let us look into the general methods of preparation of some of these hydrates. Again we can use the corresponding halides and some reducing agents such as lithium aluminum hydride. For example, SiCl4, when it is treated with lithium aluminum hydride, it leads to the formation of SiH4 silane, where in case of germanium, instead of using germanium tetrachloride, one can conveniently use directly germanium oxide, and same reducing agent can be used here, lithium aluminum hydride. This leads to the formation of germane or GeH4, and LiAlO2 is formed, and these are homolyptic hydrates. One can also make mixed hydrates containing some organic moieties. For example, when trichlorophenylsilane is treated with lithium aluminum hydride, it gives phenylsilane. There is no need to call phenyl trihydrosilane. Simply if you call phenylsilane, that means we are referring to PHSiH3 plus 3 LiAlCl4. So, in this fashion one can generate a different kinds of homolyptic silanes as well as containing some organic moieties. For example, one can also start with dimethyl dichlorosilane, and one can take appropriate amount of lithium aluminum hydride. I am not balancing this one. One can generate dimethylsilane Me2SiH2, and corresponding lithium aluminum chloride can be formed as a byproduct. And these hydrates are also called hydrocarbons, especially all this methane, ethane, propane, and here analogues are generally called as hydrocarbons. These hydrocarbons are thermodynamically unstable in air. That means suitable activation in the form of a spark is needed to ignite hydrocarbon, and essentially in internal combustion engine what we are using is we are using a spark and igniting the oxidation of hydrocarbon by incorporating or sending air into the chamber, and then what happens is we are essentially burning the fuel, or in case of automobiles it is petrol we call it, is essentially the major component of petrol is octane. Along that we also have higher analogues along with heptane and hexane, and one can look into this reaction that happens in internal combustion engine. C8 H18 is octane. When it is burnt with oxygen, to burn 1 mole of C18 H18, that is octane, we need 12.5 moles of oxygen. That gives 8 equivalents of carbon dioxide plus 9 equivalents of water plus energy. So, here one can roughly estimate by looking into the molecular weight how much oxygen is needed. For example, molecular weight of octane is 108. That means, in order to completely oxidize or burn 108 grams of octane, we need about 200 grams of oxygen. That leads to the complete combustion, and heat of combustion of octane is minus 5460 kilojoules. So, 1 mole of octane when it is burnt, heat of combustion is 5460 kilojoules. That means essentially 5460 kilojoules per mole. The mixture known as gasoline or petrol, when used in high compression internal combustion engines, has a tendency to knock. That means pre-ignition will be there. As a result, what happens? Most of bulk of fuel will be wasted. This is called knocking. So, in order to prevent this one, anti-knocking reagents are added. Essentially, tetraethyl lead used to be added in olden days, and because of its hazardous effects on environment, nowadays it is banned, and tetraethyl lead is no longer used as an additive in fuel. Instead of they are using some other mild reagents to prevent the knocking and increase the efficiency of the burning of fuel. For carbon compounds containing double and triple bonds are well known. For example, we know C double bond C, we also know C triple bond C. So, they are called alkenes and they are called alkynes. Similarly, we know C double bond O, compounds containing C double bond O, compounds containing C double bond N, compounds containing even C triple bond N, and then compounds containing C P double bond. So, these are all compounds are known, whereas with heavier elements multiple bonds are not quite common, again because of the bigger size of atomic orbitals. And for example, if you go for silicon, silicon double bond is not known. Only in order to stabilize multiple bonds among heavier elements, one has to go for very bulky substituents to prevent kinetically addition of some other smaller groups to get it saturated. So, only by having very bulky groups and by giving umbrella protection, one can stabilize element to element multiple bonds. Otherwise, it is not possible with less bulky substituents. I would discuss those things much later, and of course, nevertheless some multiple bonded compounds are known. For example, with lead, this Pb double bonded compound is known. In this one, as I mentioned, very bulky substituents are used, that is 2,6-diisopropyl phenyl groups are used. So, in this case essentially this is the first example of a Pb-Pb compound. In this one, because of the bulkiness, you cannot add another group. As a result, what happens? It will stabilize by interacting two p orbitals to form another bond, so that two bonds are there, and it is not exactly two double bonds are there. When I discuss about some of the organometallic compounds of p block elements, I would be discussing about the nature of bonding that one can expect for such heavy metal multiple bonded compounds. Let us look into the reactions of group 14 elements with halogens. Of course, tetrahalides are quite common, and tetrahalides exist for all group members except for lead tetraiodide, which is too strong an oxidizing agent to coexist with a reducing iodide. The same thing I had mentioned while discussing the chemistry of group 13 elements, that thallium triiodide is unstable, and because of the oxidizing and reducing properties of both the elements that we are bringing together. For the same reason here, PbI4 is highly unstable. As a result, it is very difficult to prepare and isolate the compound. And however, PbR, the lead tetrabromide, is known, and also this also unstable. PbCl4 is itself is unstable because of +4 oxidate of lead. However, you can make that compound, but that is highly oxidizing in nature. Then how to prepare this tetrahalide? Simply by combining the two elements one can make it. For example, silicon when combined with chlorine at high temperature, it gives SiCl4. Similarly, tin metal when it is interacted with iodine, it gives SnI2 to start with, and further addition it gives SnI4. And in case of germanium, germanium oxide is the ideal starting material. So, germanium oxide when it is treated with 4HBr, it gives germanium tetrabromide. Just to show the interaction of group 14 elements with the different halides, I have taken chlorine here, iodine here, and HBr here. And of course, SiCl4 with the excess of water, it undergoes hydrolysis to form SiO2 NH2O plus HCl. It is very interesting to compare the hydrolysis or reactivity of carbon tetrachloride and silicon tetrachloride. All halides in principle should undergo hydrolysis except SiF4 because of kinetic instability, but in contrast CCl4 cannot undergo hydrolysis. In fact, even at high temperature it does not react with water. As a result, in some cases where there is a fire hazardous is there, in some cases carbon tetrachloride is essentially used to extinguish fire. That means you can imagine how stable CCl bonds are in carbon tetrachloride, but in contrast in case of SiCl4 it is highly sensitive to moisture and readily undergoes hydrolysis to form silica. The reason is, if you look into the CCl bond strength and silicon chloride bond strength, they are essentially equal and comparable, but despite it does not react means it has to do something with kinetic stability of SiCl4. The kinetic instability comes because silicon is larger in size and also it can enhance its coordination number from 4 to 6. As that provision is not there in case of carbon tetrachloride. As a result, it does not react, whereas SiCl4 readily reacts, form silica. And of course, one can also extend the same analogy in case of SiF, sulphur hexafluoride also. Of course, sulphur hexafluoride also kinetically stable. The reason is very simple, since it is octahedrally coordinated. If you want to react with water, there is no scope to enhance its coordination number further unless 1 or 2 SiF bonds are broken. And whereas in case of silicon tetrachloride, so we have only 4 coordinated and there is no need to break 1 or 2 bonds to interact water with silicon. Suddenly it can use 5th or 6th coordination. That makes silicon tetrachloride more vulnerable for hydrolysis compared to carbon tetrachloride, which lacks that kind of expansion of coordination number from 4 to 5 or 6. So, let us look into the preparation of halides. For example, tin reacts with hydrogen halides to give SnX2 plus H2 is liberated. Similarly, GeX4, that means germanium tetrahalide in combination with germanium can give divalent halide or GeX2. This is called comproportionation reaction. I was discussing about disproportionation reaction while discussing the chemistry of group 13 elements. Now, if you see here, a germanium in +4 state is combining with germanium in 0 valence state to give germanium in +2 state. This is called comproportionation, and in contrast you can look into this reaction. Germanium iodide, it decomposes to give germanium tetraiodide plus 2 germanium. So, this is a opposite, exactly opposite of what happened here. So, this one is called comproportionation. And whereas this one is called disproportionation. That means, using either disproportionate reaction or conproportion reaction, we can interconvert divalent halides into tetravalent halides or vice versa. The tin halides, I have shown the structures of tin halides here. You can see in gas phase, this is in the monomeric form. It is a discrete molecule, whereas in solid state it uses the lone pairs of chlorine to establish a bridging chloride between the neighboring SnCl2 moieties to have a one dimensional polymeric structure. And when such dichlorides are there, essentially they are Lewis acidic in nature. So, one can expect the formation of adducts very similar to boron trichloride or aluminum trichloride or boron trihydride. Tin dichloride, that is SnCl2, in gas phase it exists in the monomeric form. You can see the structure I have shown here. And you can see now, because of this one we have Sn in +2 state, 2 electrons are left on tin. As a result, what happens in solid state, it try to establish a chloro bridge, and chlorine having a pair of electron that goes to the tin, and it forms a covalent bond. So, because of this one, what happens, it will take a one dimensional chain structure in solid state, and when you have this covalently unsaturated form SnCl2 or even SnX4, especially with heavier elements where there is a provision to enhance their coordination number other than carbon compounds, one can also expand their coordination number. So, as a result, they act as sort of Lewis acids. This property can be seen in the formation of adducts in case of tin and other higher tetrahalides. For example, one such example I have shown here. If you just look into SnX4 here, let us say X is fluorine, so tin tetrafluoride. On addition of one fluoride, it takes trigonal bipyramidal geometry having composition of SnX5 minus, which on addition of one more fluoride, it forms SnF6 minus, and this is similar to SF6, and these compound also quite stable towards hydrolysis. Compared to SnX4, this is stable simply because it has coordination number 6, and there is no scope for water molecules to attack the central tin atom directly unless one or two SnX or SnF bonds are broken. For the same reason, sulphur hexafluoride is also inert towards hydrolysis under normal circumstances. However, on heating or at high temperature, when you treat SF6 or SnF6 minus with water, the breakage of or cleavage of these one or two halide bonds happens, and then your hydrolysis initiates and they undergo complete hydrolysis to give the corresponding oxides. And another interesting feature of carbon is its propensity to form extensive stable chains. The congeners of carbon, that is heavier elements such as silicon and germanium, tin and lead, do not have this kind of property, and they show less inclination towards forming stable long chains. And it is very interesting, we have very long chain carbon hydrates we call olefins. Despite there is no thermodynamic barrier, the formation of long chain silanes such as SiN H2n plus 2. For example, in case of carbon we have Cn H2n plus 2 series we have, and also we have Cn H2n series, and we also have Cn H2n minus 2 series we have. So, this kind of series not seen with heavier elements, despite it is possible to make SiN H2n plus 2 similar to alkanes silanes. The synthesis and characterization of such compounds is a very formidable task, because it is not easy to stabilize them. Catenation in case of silicon is restricted to having up to 10 silicon atoms in the chain. For example, this one is known, very similar to decane, it is decasilane is known. However, these compounds are also highly sensitive towards moisture assisted hydrolysis reactions. Although silica-silica bonds are weaker than carbon-carbon bonds, the energy difference do not account for the observed stability differences. The reason is the low energy decomposition pathways that are available to silanes that I told you, because it can enhance its coordination number and readily one can break Si-Si bond or tin-tin bond very readily, but that is not true in case of carbon-carbon bond. They are very strong and it is not easy to break CC bond, and hence in petrochemical industries the CC bond breaking, or we call it as cracking, is a very tough task, and this essentially cracking is carried out using heterogeneous catalysts at very high temperature. You can see in this slide the comparison is made between the hydrates of carbon and silicon. As I mentioned, in addition to their kinetic instability, silanes are difficult to handle because they are very reactive compared to hydrocarbons. In fact, both the reactants are thermodynamically favored to proceed to the right. The major differences not apparent in the stoichiometric reactions is the energy of activation, which causes the paraffins or alkanes to be kinetically inert, in contrast to related or analogous heavier element hydrates such as silanes. Further complications with silanes arise from lack of convenient synthetic methods and also the difficulties we face in separation, because we cannot use ordinary means of column chromatography and other purification methods in case of silicon hydrates or silanes. And however, compounds having 1 to 8 silicon atoms in a chain are known, but as I said, they are highly reactive. And germanium, in case of germanium, Ge9H20 is known, and in case of tin only SN2H6. So, analog of alkane, that is ethane, is known, and a wide range of alkyl and aryl compounds of silicon, germanium and tin and lead have been prepared. For example, trimethyl tin chloride or tetraethyl lead, and halides with EE bonds are also known, that means catenated halides, that means having carbon-carbon bonds instead of having hydrogen on it, having halides. Similar to extensive range of hydrocarbons, diverse range of halocarbons are also known. Best example and finding numerous applications is PTFE. PTFE, this is nothing but polytetrafluoroethane. ethene, and is an extremely stable polymer finding numerous application in day to day life. I have shown here the catenated carbon fluorine containing compound. It is polymer, and of course, one can make in case of silicon also. You can see here each carbon is tetrahedral having 2 fluorine atoms and 2 carbon bonds, and this has this one dimensional chain like structure. And for silicon, a large number of higher halides are also known containing chains of silicon atoms analogous to polysilanes. Germanium, tin and lead form very few such analogues because of their low stability of EE bonds, that is SN-SN bond or PB-PB bond. And we know that as we move down the group, the reactivity of most of the bonds, whether you take element to oxygen bond, element to hydrogen bond, element to chloride, halogen bond or element to carbon bond, the reactivity increases. As a result, it is very difficult to make and isolate those compounds. When carbon or silicon is heated with many metals, the corresponding carbides and silicides are formed. When carbon or silicon are interacted with highly electropositive metals, we get ionic carbides and ionic silicides, whereas with the transition metals we get essentially carbon or silicon atoms included in the interstitial spaces, very similar to what we saw in case of graphite having potassium inclusion compounds. And here transition metals typically form such interstitial carbide compounds in which the individual carbon atoms occupy holes in close packed metallic lattices, and these materials are also very hard. That means, addition of a small percentage of carbon or silicon makes the metals much harder. For example, if you look into the steel, it contains anywhere between 0.05 to 0.25 percentage of carbon, whereas stainless steel we use as utensils and in other applications have about 0.1 to 1% of carbon in it. And some interstitial carbide of electropositive metals readily gives hydrogen and hydrocarbons, but others hydrides, other carbides such as tungsten are very hard and inert materials. In fact, tungsten carbide is very hard and it is used in cutting tools. Where it is not possible to use diamond, carbides of reactive metals tend to be ionic in nature. I had mentioned mostly with electropositive metals such as alkali metals and alkaline earth metals. For example, if you take Na4C, where 4 hydrogen atoms being replaced with sodium, or Be2C, where carbon is bound to 2 beryllium atoms through 2 double bonds, formally contain carbon C4 minus ions, and which on essentially hydrolysis gives methane. That also I showed you in my one of my previous lectures while discussing the chemistry of alkali metals as well as alkaline earth metals. When others contain acetylides and give, for example, if you have acetylene containing Ca2 calcium carbide like CaC2, it gives ethane or acetylene on hydrolysis. Let me repeat those reactions again here. For example, take calcium carbide and treat with the 2 equivalents of water, it gives acetylene and calcium hydroxide will be formed. Similarly, lithium carbide on hydrolysis gives propane, 1 propane plus 4 LiOH. That means ionic carbides are sensitive towards hydrolysis and readily give the corresponding hydrocarbons and hydroxides. Let us look into group 14 element oxides. Oxides of carbon being gases are quite different from those of other group 14 elements. For example, silica SiO2 is a solid with very high melting point having 3-dimensional structure, and structural differences results from the presence of strong p-pi bonding between carbon and oxygen, and we can see carbon carbon double bond and also carbon oxygen double bond, whereas carbon oxides are essentially discrete, whether you consider carbon monoxide, carbon dioxide or even carbon suboxide. I will give you the preparation of carbon suboxide later. In contrast, silicon to oxygen double bond is unstable. We do not have any example of any compound having silicon to oxygen double bond. This is because of the mismatch of p orbitals of silicon and oxygen that should lead to the formation of a pi bond. Since because of mismatch one cannot form readily silicon to oxygen double bond, and however, it prefers to have 2 silicon to oxygen double bond in its place, and silicon oxides and many oxyanions of silicon have infinite covalent network structure having numerous SiO bonds. Heating the element in oxygen forms the dioxide. Directly heating the element with oxygen leads to the formation of dioxide. And let us look into the different type of oxides we come across. In case of carbon, we have CO, CO2, and also another one called C3O2. This is called carbon suboxide, and carbon monoxide can be readily generated in laboratory by dehydration of formic acid using sulfuric acid. It essentially forms CO and H2O comes out. If you take formic acid and treat with concentrated sulfuric acid, CO gas comes out with the formation of H2O, and carbon monoxide is poorly soluble in water and does not react with it. CO plus OH gives HCO 2 minus. Format anion when concentrated with concentrated hydroxide it gives. So, CO is isoelectronic with N2 and has very similar physical properties, and also you know the fact that carbon monoxide is very poisonous and it is much more reactive than nitrogen. It combines with halogens directly, for example, iodine or chlorine to give highly poisonous gas called phosgene. So, this is called phosgene. It is highly poisonous, and of course, we all know the fact that carbon monoxide is an excellent ligand in coordination chemistry to stabilize transition metals in their low valent state. We have several homoleptic carbonyl compounds are known. For example, the first one to be known is nickel tetracarbonyl. We have group 6 element carbonyls such as chromium, molybdenum, tungsten hexacarbonyls, iron pentacarbonyl, and also we have carbonyl clusters such as Ru3CO12 or iridium 4CO12, etc. Of course, this is a extensive chemistry is there behind metal carbonyls. CO compares very nicely in terms of its donor and acceptor properties with phosphines. So, I will talk to you about utility of phosphines as ligands in coordination chemistry, organometallic chemistry, and also homogeneous catalysis when I discuss the chemistry of group 15 elements. And the other oxide, carbon dioxide, is the most stable oxide that is produced on enormous scale industrially by the combustion of coal, oil and natural gas. In laboratory, one can conveniently prepare by heating calcium carbonate. This gives calcium oxide and CO2 is liberated, and CO2 is soluble in water mostly as dissolved carbon dioxide molecules, but a small amount of CO2 is hydrated to give carbonic acid, that is H2CO3, and this is a weak acid partly dissociates to hydrogen carbonate, that is HCO3 minus or CO3 2 minus carbonate. And for example, sodium oxide, when it is treated with carbon dioxide, it readily forms sodium carbonate. In the same way, hydroxide, if you take and treat that one with carbon dioxide, any hydroxide, it gives the corresponding carbonate with the formation of water. Calcium carbonate, when it is combined with carbon dioxide, plus water, it forms calcium bicarbonate. So, this equilibrium is very important in geochemistry. For example, the deposition and redissolution of limestone rock during weathering. That means, this equilibrium whatever I have written is very important in geochemistry. For example, the deposition and redissolution of limestone rock during weathering. Then carbon suboxide I was mentioning, that can be prepared starting from malonic acid. This is malonic acid having 2 carboxylic groups using a dehydrated agent such as P4O10. So, this is called carbon suboxide. This can be conveniently prepared by treating malonic acid with phosphorus pentoxide as a dehydrating agent. It abstracts 2 equivalents of water to make this C3O2. When you look into the structural aspects of silica, that is SiO2, it is extremely complex. The stable form of SiO under ambient condition is quartz, and other high temperature modifications such as tridymite and cristobalite all are also known. The different ways of linkages shown by SiO4 tetrahedra results in a variety of silica structures, and also a vast number of polymeric silicates occur naturally. In case of germanium and tin and lead, we have germanium oxide, tin oxide and lead oxide have considerable ionic character and all of them adopt rutile structure. That means, their structures are very similar to titanium oxide. Of course, titanium oxide is called as rutile or rutile, and 6 coordinated metal and 3 coordinated oxygens are there in the rutile structure. In the same way, here in the solid state, germanium, tin or lead are 6 coordinated, whether the oxygen is 3 coordinated. I will show you that one in a couple of minutes. These oxides are essentially amphoteric in nature and dissolve in both acids and bases. Hydrated SN2 plus and Pb2 plus ions undergo substantial hydrolysis. You can see here in this slide, the blue color spheres mention group 14 elements such as germanium, tin or lead, and oxygen is shown in red, and oxygen you can see this is 3 coordinated, whereas these group 14 elements are 6 coordinated, and of course, here I have not shown the 6 coordination, but yeah, you can see here this central atom has connected to 6 oxygen atoms in an octahedral fashion. And the next one is sulphides. Among sulphides, carbon disulfide is a molecular substance that is very similar to carbon dioxide. CS2 is a molecular substance similar to carbon dioxide. The species CS, sulfur analog of CO, is unstable as a free molecule, but can be stabilized by coordination to a metal. For example, in case of CO, we have a triple bond. If you think of similar triple bond between carbon and sulfur, it is not possible because of again mismatch of the orbitals that are supposed to overlap to form this multiple bonding as a result. However, CS is not known, CS2 is known. CS2 is very similar to CO2. As I said, CS is not available in the free form, or it is very difficult to isolate in the free form as a free molecule. However, CS can be generated in situ starting from carbon disulfide or any other source of CS, and can be used as a ligand very similar to carbon monoxide in metal complexes. Of course, several transmetal complexes containing CS are known. One such example is RHCl CS PPH3 2 times. So, here we know the carbon monoxide analog is known, for example, RHCl CO PPH3, this compound is known. Bis triphenyl phosphine chlorocarbonyl rhodium, and here CO can be conveniently replaced by CS. Of course, not one can do directly replacing or doing substitution reaction of CO with CS. There are easy methods are there. For example, you all know Wilkinson catalyst, it is chloro tris triphenyl phosphine rhodium. This one, when it is treated with carbon disulfide, what happens? It forms this compound. So, now one of the triphenyl phosphine comes out as triphenyl phosphine sulphide. So, here one of the sulfur from the carbon disulfide is abstracted by phosphorus being a Lewis base. It undergoes from +3 oxidate to +5 oxidation state, and thus abstracting one leads to the in situ generation of carbon sulphide that reacts with rhodium to form this compound. So, there are several methods to make those things. The compounds with in case of other heavier elements, for example, Me, where M is group 14 element and E is group 16 chalcogen. Since we are discussing the chemistry of oxides of group 14 elements, we are also known, these kind of compounds are also known, where E is sulfur, selenium or tellurium, and M is germanium, tin or lead. So far we discussed about the oxides of group 14 elements. While discussing, we looked into various forms of oxides. Carbon shows variety, it forms carbon monoxide, carbon dioxide and also carbon suboxide. In case of silicon, it forms only silicon dioxide SiO2 having single SiO bonds, whereas in case of germanium, tin and lead also we make the corresponding oxides. And In case of sulphides also, divalent sulphides are also known. I will discuss more of these in my next lecture. Thank you very much.